Okay, so welcome back to this next video on transformations of trivariate random variables and beyond. Okay, we got by the end of last video that if you want to take a little vector in your domain, and you want to know what is it transformed onto by your function f in the codomain, then the way you can do that is you can multiply your vector by this matrix of partial derivatives. And now something very, very important I want to emphasize from this is that if you have a vector in your codomain, if you start off with a vector in your codomain, let's say v bar here, so you start off with some vector in your codomain and you want to transform it back into a vector in your domain, then the way that you would do it is you take the inverse matrix of this and multiply it by your vector in the codomain to get back your vector in the domain. So that's going to become very, very important later. Right, okay, so for now what we're trying to do is we're trying to, here is our picture of R3 again, so here is our point x, y, z, and we had this box, remember, here, so this was this box, and it was formed by the span of these three vectors that we had here. So we had one vector which was delta x in the x direction, 0 in all the other directions, one vector which was 0 in all the other directions and delta y in the y direction, and one vector which pointed in the z direction, and that had delta z in the z direction and 0 in all the other directions. Okay, and we wanted to basically transform those vectors onto what they will be in the codomain over here. So we have some point which is x bar, y bar, z bar, and I'm too lazy to write the x bar as a function of x, y, z, so it's understood that that's what that means. And we're going to transform these vectors onto what they are over here. So they'll be like this. They might not form a box anymore, and we want to take what their span is, i.e. what the shape they span is. We want to know what the volume of the shape which they span is over here, i.e. what does this volume, this original volume, which is delta x times delta y times delta z, get transformed onto by this function f? Okay, right, so we just now need to transform these vectors and then take the volume in the way that we've seen in previous videos how to do. Okay, so if we transform these vectors, let's start with the vector delta x. What we would do is we'd stick in v1 is equal to delta x, we'd then stick in v2 is equal to 0, v3 is equal to 0, but instead of thinking about it like that, let's just go back to what we have up here, which tells us exactly what v bar is. If we just stick in v2 is equal to 0 and v3 is equal to 0, then all of these terms here are going to be 0 because they've all got v2 or v3 multiplied by them, and v2 and v3 are equal to 0. So it's only these terms at the front that matter. So this vector delta x, so let's say this vector here, which is the image of the vector delta x 0, 0, is going to be this vector here, so where we substitute in v1 is equal to delta x. So we get the partial of x bar with respect to x times delta x, the partial of x bar with respect to y, is it y? No, sorry, I do apologise. The partial of y bar with respect to x times delta x, the partial of, let me pull this up, the partial of z bar with respect to x times delta x. So that is what that vector is mapped onto. In a similar way, if we want to do what the vector delta y is mapped onto, this vector down here, let's say, I'm showing them, in the same sort of order. I put delta x here, delta y here, and delta z here, just because it makes the picture easier to understand. But of course, they could be all over the shop. They might not be in this order anymore. Okay, now what we do is we substitute in v1 is equal to 0, v2 is equal to delta y, and v3 is equal to 0. So this time, we only get these middle ones here. So we'll get that this is equal to, we'll get the partial of x bar, and I'm going to write it a different way to save space. The partial of x bar, you often see x bar subscript y to mean partial. So I'll write it that way. X bar subscript y, delta y. Y bar subscript y, delta y, so the partial of y bar with respect to y, the partial of z bar with respect to y times delta y. So that's that vector there. It looks less messy, it looks tidier. And then finally, this image of delta z, this vector here, what's that going to be equal to? Well, we set delta x equal to 0, so v1 goes to 0. We set the y component equal to 0, and now we stick in delta z for the v3. So we're going to get, using our notation again, we'll get x bar partially differentiated with respect to z times delta z, y bar partially differentiated with respect to z times delta z, and z bar partially differentiated with respect to z delta z. Okay, and all of these partial derivatives are evaluated at that point x, y, z. Okay, so now if we want to know what is the area spanned by all of these, well, we know how to do that. What we do is we put all of these together in a matrix and take the determinant of that matrix. So, and then take the absolute value. So their volume is going to equal the absolute value of the determinant of the matrix, where you put each one of these vectors in a column, basically, of the matrix. So let's begin with the x one, just to put it nicely in order. Okay, so let's put x bar partially differentiated with respect to x times delta x. Then we've got y bar partially differentiated with respect to x delta x. And then we get z bar partially differentiated with respect to x delta x. Okay. Then what we have is this one here, the delta y vector. So we'll put that in. We get x bar partially differentiated with respect to y, delta y. Y bar partially differentiated with respect to y, delta y. Z bar partially differentiated with respect to y, delta y. And then finally, this one here, the delta z vector, which is x bar partially differentiated with respect to z. Let me move this up. X bar partially differentiated with respect to z, delta z. Y bar partially differentiated with respect to z, delta z. And z bar partially differentiated with respect to z, delta z. And we're taking the determinant of that matrix and then taking the absolute value of that determinant. Now, basic linear algebra, one of the basic properties of determinants is that if you have a constant in a column like this, so if you have a constant which is present in every term of a column, you can basically pull that constant out. So, let me give you an abstract example. So, if you're taking the determinant of a matrix, let's say, I'll just do a 2 by 2 matrix. Let's have components A1, 1, and then we've got a constant C, A1, 2, A2, 1, constant C, A2, 2. So if you're taking the determinant of that matrix, it is just equal to C times the determinant of A11, A21, A12, A22. So that's a very, very well-known property of determinants. So we can pull out the delta x, but we can also pull out the delta y and the delta z. So let's pull those out of the determinant. When we take the absolute value, they're already positive. So we can pull them out of the entire thing. So let's cross them all out here and put them outside here, delta x, delta y, delta z. So this value here, this determinant of this matrix of partial derivatives, and you will notice that this matrix of partial derivatives here is exactly the same matrix of partial derivatives we had up here. Yes, I've written it in a different notation, but all of these partial derivatives perfectly stack up. Here we've got the partial derivative of x bar with respect to x, the partial derivative of y bar with respect to x, etc. They all are perfectly unanimous. So this matrix of partial derivatives, if you take the determinant of that and then the absolute value of that, that is the ratio, basically. That's how much you have to multiply delta x, delta y, delta z by, which is this original volume spanned by those vectors. So this is delta x, delta y, delta z is the original volume of this, of the span of the original vectors, and the amount by which you have to change that to get the volume of the span of the vectors in the codomain is the absolute value of the determinant of this matrix of partial derivatives. Now, there is a very special name for the determinant of this matrix of partial derivatives, which is, it's given the symbol the Jacobian of this new of this space over here, which is denoted x bar, y bar, z bar with respect to x, y, z here. So you write it like that. So that's how it's denoted, and it's called the Jacobian. So I'll write that down, Jacobian. Okay, right, so now if we are going back to our original problem then in terms of probability spaces, so our original problem was that we had some transformation t which was mapping a point x, y, z onto another point in the codomain over here. So let's say it's been mapped onto this point x bar, y bar, z bar here. And we wanted to know what was the probability density function on this space over here. So we said, let's draw a little box back here. Draw a little box here with side lengths. In fact, let me complete the little box now because it will look awful if I don't bother. So it's got side lengths, so let me draw it bigger now. Here we go. Sorry about this. Right, okay, it's got side lengths, delta x bar, delta y bar over here, and delta z bar here. Okay, and we want to know if we take the pre-image of this in this space, it will form some potentially parallelogram-like shape, but 3D. I really need to find out what the name for that solid is. It will form a shape which is spanned by the pre-image of these vectors. So you can view this vector as being the vector delta x prime 0, 0 in the y component direction and the z direction. This as being the vector 0 in the x direction, so 0, delta y bar, 0, etc. And basically if we take the pre-image of those vectors in here, there'll be some different form, that they'll look different, and we want the volume spanned by them basically. But we know the transformation in this direction, so we can construct the matrix of partial derivatives. So let's say that T maps an ordered triplet x, y, z onto x bar, which is a function of x, y, and z, y bar is a function of x, y, and z, and z bar is a function of x, y, and z. Okay? Right. So we know what the matrix of partial derivatives going this way is. The matrix of partial derivatives for transforming a vector, if you've got a vector in here, v, and you want to know what it is over here, v bar, you want to know what that vector is, then we know you can get it by multiplying it by this matrix of partial derivatives. So I'll quickly write that out. We've got x bar differentiated with respect to x, x bar differentiated, wait, which one is it? Yes, y bar differentiated with respect to x, z bar differentiated with respect to x, x bar differentiated with respect to y bar differentiated with respect to y, z bar differentiated with respect to y, x bar differentiated with respect to z, y bar differentiated with respect to z, z bar differentiated with respect to z. So that is the matrix of partial derivatives. And we know that if we want to transform a vector v from this domain into the codomain, we just have to multiply it by this vector to get our new vector. Now, if what we're doing is we're starting off with vectors over here and transforming them back and asking what is the area that's going to be spanned by these vectors here, by these vectors back here. The pre-image is of these vectors over here, okay? And we know that if we were going forward, the amount by which we'd have to alter the vector here, the ratio by which the volume would change, is given by that Jacobian, i.e. the determinant of this matrix of partial derivatives. But we know that the matrix of partial derivatives going the opposite way is just going to be the inverse of this matrix. So if you want to take vectors in here and turn them into vectors in here, you need the inverse of this matrix. So let's put inverse there, and let's make the this vector v bar and this vector v. So this will take a vector in here and turn it back into a vector in here. Now if you want to know how the volume is distorted, it's going to be the determinant, it's going to be the modulus of the absolute value of the determinant of this matrix, this inverse matrix, which I'll call here. So this, I'll call it M inverse. So let's let M be the matrix of partial derivatives. We're talking about now M inverse. So we want the determinant of M inverse. But we know from linear algebra that the determinant of M inverse is just 1 over the determinant of M. And the determinant of M is what we were calling the Jacobian, basically, of x bar, y bar, z bar with respect to x, y, z. So this is just going to be 1 over the Jacobian of x bar, y bar, z bar with respect to x, y, z. I.e., if you now get rid of this inverse here and just take the determinant of that matrix, evaluated at this point x, little y, little z, which is the pre-image of the point x bar, y bar, z bar, then that's the amount by which you have to change this area, delta x bar, delta y bar, delta z bar, to get the area, volume, you know what I mean. The amount by which you have to alter this volume, delta x bar, delta y bar, delta z bar, to get the volume spanned by those vectors. So the new volume basically is going to be this correction factor here times our old volume, delta x bar, delta y bar, delta z bar. Okay, so if we now want the probability that you're within this little box at this point x bar, y bar, z bar, we've said that the probability density function of this joint random variable x bar, y bar, z bar evaluated at x bar, y bar, z bar, little x bar, little x y, little y bar, little z bar, times the volume of this box, delta x bar, delta y bar, delta z bar, should be the probability that you're within that box. But the way that we can work out that probability is by saying, let's take the pre-image of this box within here, and then just times that area, times that volume rather, by the probability density function on here, which is the probability density function x, y, z, so the original random variable x, y, z, evaluated at the point little x, little y, little z, where we define little x, little y, little z to be the point which is the pre-image of x bar, y bar, z bar in this transformation T. Okay, then all we do is cancel these delta x bar, delta y bar, delta z bar on either side, and we get that the way in which we would transform a joint random variable, a trivariate random variable, is that the new probability density function evaluated at a point x bar, y bar, z bar is equal to 1 over the absolute value of the 1 over, because you can take this absolute value sign down, because the absolute value of 1 is just going to be 1, so it's 1 over the absolute value of the Jacobian of x bar, y bar, z bar with respect to x, y, z, and that's evaluated at the point little x, little y, little z, which is the pre-image of the point little x bar, little y bar, little z bar in the transformation T, and then times the old probability density function of the original trivariate random variable evaluated at the point little x, little y, little z, where this point is the pre-image of this point here. Okay, so in the next video, let's just say how you would generalize it to a higher dimension. In the higher dimensional case, all that changes is that this Jacobian becomes the Jacobian for a higher dimensional case. So the matrix of partial derivatives gets bigger, basically. You add on another variable, so let's say t, So you'd have t down here, and you'd have another t bar down here. So you can add on more variables, basically. So the matrix of partial derivatives gets bigger, but again, you are just taking 1 over the Jacobian, which is just the determinant of this matrix here, evaluated at the point little x, little y, little z, etc., which is the pre-image of your point little x bar, little y bar, little z bar. So basically it just becomes the same formula, you're just dealing with higher dimensional cases.